Good afternoon and welcome to our AP Physics 1 review session. My name is Joshua Beck. I'm coming to you from Clayton, North Carolina. I hope you guys enjoyed your weekend. I know I did. It was very productive, got a lot of stuff done, and we've got a busy week scheduled for you guys here as well. I know that some of you are new viewers tuning in to watch our videos as we go over some of our recent free response questions. For our previous viewers, those of you that watched Friday's lesson, you know that I left you with a practice problem at the end of class. I'm actually going to save that for the end of class today. So that way, if you were part of class on Friday and you want to stick around for the last few minutes of today's lesson, I will be happy to go over that. But today I actually want to kind of jump into our free response analysis. Over the past couple of weeks, Greg and I have been going through some review sessions. These are the topics that are going to show up on the 2020 exam. If you haven't had a chance to go back to these review sessions, if you missed them live, that's okay. They're recorded. Some of you have been watching the recorded versions. Feel free to go back and check these out. These are our sort of topical reviews. Now, keep in mind, these are not anywhere close to being comprehensive. It's just kind of an overview of some things that Greg and I wanted to try and present to you guys. But feel free to go back to these different units. These videos should be available on YouTube. Again, not for a comprehensive, but at least kind of an overview of some of these general concepts. What we're going to be looking at today, and then throughout the week and then into next week as well, is we're going to look at some of the previous free response questions. The questions on the 2020 exam are going to fall into these these categories here. But some of you may be tempted to only review these types of questions from the old exams. You may say, oh, well, I only have a couple paragraph style questions, or I only have a couple QQT style questions. So let me just review those. And any other question, whether it's an experiment or this or that, I don't need to review any of those things. But keep in mind that all of these questions are going to be good practice. They're all going to require sort of a variety of skills that will be used on these questions on this upcoming exam. Now, my goal over the next several lessons is to help give you tips, hints, techniques, things like that, that I would use. Now, you may have different techniques, you might prefer a different method, and that's totally fine too. I just want to present some ideas that I have. Remember that these questions will be graded by physics people. So even if your methods may vary a little bit from mine, or you phrase things a little bit differently than the way that I do, they're still graded by physics people. So they'll still recognize good physics and good explanations. But they're also not allowed to interpret what you said. So you need to be careful. The people grading these exams aren't allowed to assume what you really meant. Right? So if you say something that's close but not exactly right, keep in mind that those graders, as much as we'd love to give you the benefit of the doubt, we can only grade you based on what you put down on the paper. So be deliberate with your answers to these questions, right? Pick a side and go. Don't contradict yourself. Try not to be vague, right? And just be very deliberate with your word choices, be very deliberate with your explanations, okay? See, when we grade these exams, we see a lot of ambiguity. So some things that can help you kind of clarify what you're trying to say is, instead of saying things like it, just say what it is. Are you talking about the ball, the sphere, the cart, the object, the person, the track, right? Instead of just saying change, be more specific. Is it an increase? Is it a decrease? Right? You can prep yourself for these explanations by practicing using careful word choice, and also making sure that you have a really solid understanding of the differences between words, right? You may be careless and you might use velocity and acceleration interchangeably, but they mean two different things. So being specific and making sure you're using the correct word will help make sure that you can get all the points possible for your explanations. Now, my goal here is I want to help you be accurate, but I also want you to be efficient. See, using more words is not always going to be the better method. So College Board provides a big list of these different task verbs. You can see them here, you can see them here. I'll bring up the specifics as we need them throughout the review sessions. But I know that some people are starting to look at these words and say things like, all right, well, sketching, drawing, free body diagrams, graphs, things like that. There's no possible way this can be on the exam, right? This exam, I have to be able to type everything, so they can't give me a graph. Like today's review problem involves making a graph. Well, surely there can't be a graph on this. Well, I don't want you guys to focus on trying to game this exam. I want you to think about just how much you can actually express in words, probably more than you realize. So if you have to create a graph, well, sure, you might not be hand drawing something, but could you describe that line to me? Of course. You could just simply say, this is a straight line with a positive slope. Okay, well, what if I need to compare it to this line? That's also a straight line with a positive slope. But I could just say that it has a greater slope or a steeper slope. What about this? That's a straight line with a negative slope. Could I describe something like this? That's just a horizontal line, or you could say a slope of 0. What if it curves? Could I describe this? Sure, I could say that it curves with a positive slope. Now, how would I differentiate that from that? That curves with a positive slope. So over here, I'd say it curves with a positive slope that increases. Over here, I say it's a curved line with a positive slope that decreases. You see, you can explain a lot of the things that you would normally be drawing. I know some people have asked, well, what about free body diagrams? They obviously can't put free body diagrams on there. Well, maybe not in the traditional sense where you're hand drawing these diagrams, but you should still be able to describe them. Look at this one on the left. Could you describe this? Sure, I'd say there's a normal force going up. It's the force of gravity going down, and then there's a friction force to the left. How about the second one? I've got mg pointed down. I've got tension pointing up. There, I've just described these. Oh, I could even be more specific, and I could say the tension is pointing up with a larger magnitude than mg. See, I can describe the free body diagram on the right. mg is pointing down. Got tension 1 pointing up and to the left. I've got tension 2 pointing up and to the right. So don't try and game this exam. Instead, I want you guys to focus on what skills do you have? What can you do? And then just how can you explain these things? So today we're going to look at this problem. It's the 2019 question 1 from the main operational exam. So this is the first picture. Now, something that I like to do when I start a free response question is just do a quick sort of mental overview. Just kind of look, what is it that I see? When I look at this diagram, I see a lot of useful information, right? I see a plunger over here. That's going to tell me that there's going to be some force applied. Now, from there, I might do some sort of Newton's second law analysis. A force applied for a period of time, I might be looking at an impulse and looking at a change in momentum. I may be looking at some sort of energy analysis. I don't know exactly yet, but just the moment that I see that, all these things start going through my mind. Okay, I've got forces, and then I know that I can take forces a variety of different ways. What else do I see? Well, I see something's funky about this surface right here. That tells me the surface might be different between C and D. Maybe there is friction there, and there's not friction at the other places, or vice versa. I also see a second block just sitting here. This second block, ooh, that tells me, hey, you know what? I bet there's going to be some sort of a collision. So I may need to analyze some sort of momentum conservation. So these are not things that I would necessarily label on the diagram up front, but they're just quick things that go through my head when I see this diagram. So here's the actual prompt. And I'm going to go sentence by sentence because when I see the prompt, there's useful pieces of information in there as well. When I see two identical blocks, what does that tell me? If they're identical blocks, that tells me that the mass of one is going to equal the mass of the other. This is going to make the problem a lot easier for us. Now they're placed on a horizontal surface. Great. It tells us that it's all frictionless except for this region. See, I knew it. I knew there was something different there. Here I have some frictional force that could be applied. I don't have any friction that I have to worry about at any of the other segments. Then I keep reading. It says, beginning at time TA, the block is pushed with a constant horizontal force. Okay, cool. So there is going to be a constant force. A constant force means there'll be a constant acceleration for this block. It'll experience a uniform acceleration. Now I see that upon reaching point B, the block loses contact with the plunger. So that means from here to here, I'm going to have this uniform force. But once I get to here, that force is going to drop down to 0. Okay, so I only have that applied force from A to B. Then I keep going. It says block 1 collides and sticks. I knew it. There's going to be a collision. So here I've got an inelastic collision that's going to take place between 1 and 2. And it tells me that eventually these will pass point F. So that tells me that even if my speed changes throughout this particular path, I have enough energy that it's still going to get all the way past point F. All right, so let's jump into the actual problem. The problem has you sketch a graph. So I want you to read this. You're going to sketch the speed of the center of mass of the two-block system as a function of time. On your paper, I want you to take a minute here. I'm going to give you about 45 seconds. I'll keep an eye on the timer. Give you about 45 seconds, and I want you to sketch your graph. This is important. I want you to actually take a minute and sketch a graph so that way you can see if you fall into any of these common pitfalls that other students fell into when they took this exam. So I'm going to put a little timer over here on the side. I'm going to watch it. I'm going to give you about 45 seconds to sketch your graph. Got about 15 seconds left. All right, so you should have your graph sketched. Now, again, you might be saying, well, why am I practicing sketching a graph? There's no way a graph's going to show up on this exam. Don't worry about what may or may not show up on the exam. Worry about what skills do you have. If you have the ability to make this graph, then you have the ability to describe what this graph looks like. So here's how I want to go through this. This is a little bit different. I want to actually go through this piece by piece, and I want to describe the motion and then describe what that portion of the graph would look like. All right, so starting with from A to B. Describe the motion. If we had to describe the motion of this, because this is what's going on in your head as you go to make the graph. You don't want to just create these graphs based on a hunch, or I've seen a graph that looks like this. Let me just kind of mimic that. No, you want to think about what is actually happening, and then how can I portray that in a graphical form? So between A and B, describe the motion. Well, it starts at rest, and then this plunger is going to push it, and it's going to pick up speed. So if its speed is increasing, we call that an acceleration. But we know that here, I'm going to say something more specific than just an acceleration. There's different types of accelerations, right? If I was using a traditional ideal spring where I get a different force at different lengths, then I would get a different or a varying acceleration throughout this. We talked about that end of last week. But here, this plunger applies a uniform force, so I'm going to get a uniform acceleration. A uniform acceleration is more specific than just an acceleration. Now, why is my acceleration uniform? Well, because A equals F net over m. And I'm told in the problem that I have a constant force. Now, what would I draw this like? Keep in mind, we are drawing a velocity time graph. One of the first places where people are going to go wrong is they're going to try and draw a position time graph. Make sure you're careful. Make sure you're aware of what they're asking you to draw. Okay, so a velocity or speed versus time graph in this case. So what would this look like? Well, a uniform acceleration, that means my speed's going to be increasing from 0, and it's going to go up and up and up and up at a steady rate. So if I had to draw this, I'd have something kind of like that. But how could I describe this? Because I need to be able to put this into words, right? So I would just say that this is a straight line with a uniform positive slope. Does that describe that line? Is it a straight line? Yes. Does it have a positive slope? Yes. And is it a uniform slope, meaning the same slope throughout? Absolutely. How about from B to C? Now the plunger is no longer being applied. So my net force now is going to be 0. So that means that my acceleration is 0. So if I had to describe that motion, I'd say the acceleration is 0. Does that mean that the object stopped? No, it's just in dynamic equilibrium. So it's just moving with a constant speed. Well, remember, we're making a speed or velocity versus time graph. So whatever the value is, it's going to stay at that value. So my line should look like this, but how could I describe that? If I can't draw it, I have to write it or type it. How do I describe this? Well, this is just a straight horizontal line. There, I've just described it. Let's move on to part C. Part C, we encounter some friction. So we now have a net force again. All right, we're going to experience some acceleration here because of this net force divided by the mass, Newton's second law. The net force in this case is not the force of the plunger anymore. It's this frictional force, which is in the negative direction. It's opposing all these positive velocities that we have. So what is that motion going to look like? It's going to be slowing down, but it's still a uniform rate. So it's a uniform negative acceleration. It's slowing down. So I'm going to draw a graph that goes from a higher velocity down to a lower velocity at a uniform rate. Now, how do I describe this? Well, this is still a straight line with a uniform negative slope to represent the uniform negative acceleration. Whoop. And then from D to E, well, from D to E, this thing is cruising along. So we have a net force of 0 again. This is just like B to C, except for it's going to be going a little bit slower than it was from B to C. So here my acceleration will be 0. V is constant. So we get a line that looks like this. But it is going to be slower than it was from B to C. Why? Well, because it slowed down a little bit when it went through that patch of friction. So how could I describe this? A straight horizontal line, just like I did for B to C, but a little bit lower. Now what happens at E? E is where the problem gets interesting. And I got to be honest, E is where most people started to lose points, right? Because what happens at E, you say, all right, great. I've got this collision about to take place. And I know my law of conservation of momentum. It's going to be set up like this. The initial block is at 0. They're going to stick together. So I get this over here. And I can say, all right, well, now that they're stick together, this has been doubled. So this is going to be cut in half. Cool, got it. So now on my graph, I had this velocity from D to E. So I'm going to drop that velocity down. And you might even be on the right track and say, ooh, and I know not only is it going to be less, but it'll be half. So I'm going to be really careful. I'm going to mark it out on my graph and mark out half. Ooh, I'm excited. And unfortunately, that's what a lot of people did. And if you were asked to graph the velocity of block 1, then you'd be correct. But let's take a look. What are we actually asked to graph here? We're actually graphing not the speed of block 1, but the center of mass. Whoa, wait a minute. So do I have to go back and change everything else? Well, let's take a look. This is where one block is. This is where one block is. The center of mass of my system initially is at point C. Equal masses, so even distribution. Now, once block 1 moves to here, this is block 1, this is block 2, the center of mass is right there. You can see that the center of mass has moved. Now, you may notice block 1 during that time moved from A to B. You can see the center of mass moved by half as much. Now, once block 1 gets here, that's where block 1 is, the center of mass would be right there. You can see again, block 1 moved that full increment from B to C, the center of mass moved half as much. Then once block 1 is here, you can see that the center of mass will be right there. So the center of mass keeps moving, and then once block 1 hits here, the center of mass is right there. So my center of mass moved like this. Now, at different speeds, at different times. Now, all the way up until point E, the fact that block 1 is the only one that's moving means that any sort of qualitative changes to V1, like if V1 is all of a sudden going faster, well, then the center of mass will be moving faster. If V1 is all of a sudden going slower, well, then the center of mass of the system will be going slower. So up until this collision, the only part of our system that's moving is block 1. So any qualitative changes, whether it be increases, decreases, or if it stays constant, then we would see the same thing with our center of mass. So everything that we've done so far works. Okay, we don't have value, we don't have numerical values over there. We're just looking at, okay, is the velocity increasing, decreasing, or staying constant? So all of that still holds true. Where we're going to run into issues is during the collision. See, during the collision, we have internal forces, right? It tells us the system is the 2-block system. So when one block hits it, we've got internal forces. If you go back to our conservation of momentum review session from last week, you'll notice that these internal forces will create an increase in momentum for one part, but an equal decrease in momentum for the other part. So the total momentum ends up being the same. So if I have internal forces, then the change in momentum of my system as a whole has to equal 0. Well, the momentum of my system could be calculated this way. It could also be calculated with the total mass times the velocity of the center of mass. Well, if the total momentum of my system is constant because I have internal forces, well, that means this value has to stay the same. This value stays the same. So this value has to stay the same. So whatever speed you had on your graph at point E, you need to keep that same speed on your graph all the way to point F. Yes, there's a collision there. Yes, the speed of cart 1 will slow down at that point, but the center of mass between that system will still be moving at the same speed. So here's your graph. We've got this increase in speed, then it cruises, then we've got a slight decrease in speed due to the friction, and then it cruises. And even though the collision takes place right here, that doesn't change the speed of the center of mass of our system. So what are some common errors? Maybe you look at your graph and it doesn't look quite like this. So let's see, what are some common errors? Well, from A to B, what you need to have on your graph is you need to have a straight line with a positive slope, and you'll get the point. Does it have to go up as high as mine does? No, it just needs to be a positive slope, and it needs to be a straight line. It can't be curved. One of the common errors would be a curved line. Now, what would make something curved? Well, it would be curved if the acceleration was changing. But in order for the acceleration to change, we'd need to have the force varying. And we're told that this little plunger applies a uniform force. So that means a uniform acceleration. So we've got to have a straight line. Now, maybe your graph has the second error. A lot of people put that segment BC at 0. You knew that something was 0. You were on the right track. Yes, something's 0. The acceleration is 0. But that thing isn't going to just stop. Just because the force is no longer being applied, it's on a frictionless surface. It's already moving. It wants to continue moving, and it will. So V equals 0, or A equals 0, but V does not. V is just constant. So wherever this one left off, you need to keep that one there. Now, what if your graph, what if you only went to there for the first segment? That's fine. Then your next segment needs to be right there. It just needs to pick up wherever the other speed was. Now, a lot of people have curve during CD. Curve during that CD increment is the same issue with curving AB. In order to curve this graph, you need to have that would indicate a changing acceleration, which would require a varying or a changing force. Now, the frictional force is all of a sudden there. It wasn't there, now it's there. And then once that frictional force is being applied, it's the same frictional force throughout. So whatever this acceleration is, this negative acceleration due to the friction, we need to have that negative slope, and it needs to stay the same. Now, again, what if your graph wasn't all the way up there? What if it was here? That's fine. You can put your line segment there. That's still good. That'll still get you the point. You just can't bring it to 0, right? Like I can't bring this line to 0. Or if your graph was here, you can't bring that one to 0. Now you might be saying, well, but isn't friction capable of stopping something? Yeah, absolutely. But remember, this isn't the what if game. This is a specific problem that was given to you. It's a specific scenario for you to analyze. The what if game, sure, it could. Is there a scenario where there's enough friction where it stops something? Of course, yeah, of course. But that's not this problem. And in this problem, they told you that it continues all the way past point F. So you can't bring it to rest, because if you bring it to rest at point D, there's nothing to get it moving again past there. So that violates this particular scenario. So you're no longer describing this scenario. And then, of course, the most common mistake I would say that showed up on this would be a drop in velocity here. And people say, well, this is going to have to drop immediately, slowly, however you want to do it. Any drop here is not going to follow what you're actually graphing. Again, if you were graphing V1, then yes, there'd be a drop, but you're graphing the center of mass, and that center of mass of my system is moving at a constant rate the whole time, because all of the forces during that collision are going to be internal forces. Okay, excuse me, the velocity of the center mass is not moving at a constant speed the whole time. There are things that change that, but during that collision, whatever the velocity of the center mass was, that collision has internal forces, so that will not change the speed of the center mass at this collision point. Okay, if you have any questions about this part of it, please feel free to reach out to me on Twitter, and I can do my best to help answer those. So let's move to the next part. I don't know if it's part B. Now we've replaced something. There's no more mass over here. And if you'll notice here, we've got a sphere. Ooh, sphere. Okay. I bet it's going to roll. All right. So we read through this and it says that the sphere loses contact with the plunger. Same thing. So we get the force all the way through here. We still have no friction from B to C. And then here we do have friction. All Okay? And so then the question says, which interval or intervals, if any, does the sphere's angular momentum change? Well, let's be careful before we move on to this part. What are you being asked about? I'm being asked, are there any points where the angular momentum of the center of mass changes? Okay, so angular momentum. I need to see, does it have any angular momentum and does it change? All right. So here's the rest of this problem. Here's how it's set up. It gives you these check boxes from A to B, from B to C, so on and so forth, and explain your reasoning. Now, I mentioned this maybe 2 weeks ago in one of my lessons. If I have a checkbox and then an explain your reasoning, what should I do first? Well, my preference is to do the explain part first. If you go and check a box or check a couple boxes based on a hunch, and then you try and explain it afterwards, you're setting yourself up to potentially change what you would have written just so that it does actually match the answer up above. Or you just write something and it doesn't match the answer up above and you never change it. You never think to go back. You're like, oh yeah, no, I did it. Instead, do your explanation first and then check the box. That way you'll know that your reasoning lines up with your answer. Okay. Now here's the College Board definition for what does it mean to explain. The gist of it, write a sentence or two. Okay, you need to write a sentence or two. This is not a big long paragraph, it's a sentence or two, but it's important that you connect the dots. See, the problem gives you some information and then they give you a question. So the information that's given, there's information about how the initial force is applied, there's information about the surfaces, and then what changes at different points, and then they're asking you about angular momentum. So your explanation in a sentence or two should connect the premise of the problem, so the important details of the problem, to a change in angular momentum. A lot of explanations we get are incomplete. They don't connect the dots. Or they start to connect dots that are way over here and then they never bring it back to the actual question. Or they start connecting dots from an arbitrary point that doesn't start from what the problem gives them. So you need to take the information in the problem, take the question that they're asking you, and then connect any dots in between. Now, the more efficient you can be, you'll have less dots. You may end up kind of off on a tangent and then try and bring it back. So try and think about it first. Now, before I give you my explanation, I'm going to show you some common explanations that we might see. I want you to take a look. Somebody might say friction acts on the sphere from C to D. This is true. It's great. Just because it's a true statement doesn't mean it's a complete explanation, right? Does friction act on this from C to D? Yeah. And actually, that's important. But does that connect the dots? What were we asked? We were asked to identify anywhere that the angular momentum changed. Does this connect that dot? No. And you might say, well, yeah, but in my head, what I meant was then this and then this and then this. Well, that's great. But the person grading your exam can't just interpret what you meant to say or what you thought. They can only grade what you put on the paper. So somebody might say, oh, well, friction makes things rotate. Okay, in this case, yes, the friction that this sphere encounters at point C will in fact make this rotate, and that is crucial to answering this problem. But that statement on its own, that's not enough for an explanation. Because on its own, this statement's not always true. This isn't a physics fact, right? Friction doesn't always make things rotate. The block in the beginning one wasn't rotating. So this statement on its own isn't a complete explanation. You say, oh, all right. Well, I remember from things rolling down a ramp, friction changes the angular momentum. Okay, it can, and in this case it will, but this statement on its own doesn't always apply. So I want to try and start my explanation with some sort of a factual statement, some sort of law, some sort of principle, something that's always true, and then apply the specifics of this problem to it. So in this specific problem, yeah, friction will play a role, but this statement on its own is not always true. It's not a fact. It's not a law. It's not a principle. Okay, somebody might say, again, these are discrete individual statements. Somebody might say the angular speed changes from C to D. Again, this is true, but the problem didn't tell us that the angular speed changed. The problem isn't giving us information about angular speed. So when I say you need to connect the dots, you need to take information that's given in the problem and connect dots to get it to the answer, or to answer the question. Well, angular speed does change from C to D, but that's not this dot. That's not the starting point. That's a dot over here. So you didn't connect the premise of the problem. Okay, great. So from C to D, the angular speed changes. But why? You need to take the information in the problem and connect the dots to get it to answer the question. Ooh, here's a popular one. Friction decreases VCM. Okay, that's true. It's an external force that decreases VCM, which is a change in momentum. Yep, except for this problem asks about angular momentum, not linear momentum. Okay, fine, I'll modify it. Friction decreases VCM, which is a change in angular momentum. See, now you're in trouble, because if you're talking about the velocity of that center of mass, you're talking about linear velocity, you're talking about linear momentum, and you're not even addressing the rotational component here. Let me give you another one. This one's long. I'll give you a second to read this. What do you think? It's good, right? Well, yes, it's a great answer. It's thorough. It's a little long though. See, I showed you some little snippets. Those are pretty short. Most of those were incomplete. This is great, but it's far more than what's necessary for a simple briefly explain type question. Well, so how do I eliminate? How do I get it somewhere in between? If you write something like this, that's great. You've created some additional dots, but you've connected them. You've taken the premise of the problem and you've eventually answered the question. But if you look more closely, there's a whole bunch of words here that aren't needed. See, I like to be efficient. I like to save some time. Take a look at this entire first statement. The sphere has the same mass as the original block and is launched with a uniform force. Is this information anything new? Is this response bringing anything new to the table? Or is this just simply restating what's in the prompt? This is just restating information that's already been given. Now, it may be relevant, but it doesn't need to be included in your explanation. It's just restating. The track is flat. All right, just restating. It's horizontal, just restating. It's frictionless here and here. Yes, we're restating all these things. The angular momentum is determined by the rotational inertia and angular speed. That's a great statement. But be careful, what you've just done is you've now just introduced two new variables. The question asked you about the angular momentum, but now you've just introduced I and omega. So now you have to talk about I and you have to talk about omega. You've created this sort of path that you've got to connect these extra dots. In a second, I'm going to show you how you can go straight from one to the other. So you can introduce this equation, that's fine, or this relationship, that's fine. But now you've just added more dots that you need to connect. Now they said the rotational inertia of the sphere doesn't change, so that's good. They say that the angular speed does change. Okay, that's good. But we still need to connect that to the problem. They finally say that it changes due to a torque created by the force of friction. Got it. So now I know why that changes. Based on the problem, I finally connected it to that dot. And then I went on this little tangent and I said, okay, that torque created by the force of friction changes the angular speed. And because I is the same and angular speed changes, then angular momentum will change. That's great. But there's a lot of extra words in here. Right, there's a lot of extra things, restating of the problem, adding extra dots. So here's how I would do this. And again, this is not the only right way. This is just my approach, my technique. Hopefully you'll find it useful. I'm going to start with a fact, a law, a principle, something that I know. What does that look like in this case? Well, here we go. To change the angular momentum. Remember, that's what the problem's asking about. Where does the angular momentum change? In order to do that, I need a net external torque. This is a fact. If I want to change the momentum or the angular momentum, I need to apply a net external torque. This is a fact. This is setting me up to connect the dots. Now, the second one, I'm going to make the connection. I can do this in one sentence. I'm going to connect to this scenario. I'm going to connect this scenario to my physics fact to answer my question. That only occurs at one place. That only occurs during C and D. The only place I have a net external torque would be between C and D. That's where friction is applied at a distance r away from the center of mass. In order to create torque, I need to apply a force offset from the center of mass. So that only occurs from C to D. So I started with a fact. To change the angular momentum, I need a net torque. Now connected to the scenario. The only place where I have a net torque is from C to D, where friction is being applied at a distance r. Now I check my box. I've got my clear, concise explanation ready to go. I've selected my answer. And in doing so, I've actually shown why it's not here, not here, not here, not here, because I said this only occurs from there to there. Now you might be saying, well, it's spherical. Shouldn't it be rolling the whole time? Well, let's see. While it's in contact with the plunger, I've got a force right here. Just going to deal with the horizontal forces. I've got a force right here. Is that force offset from the center of mass? No. So will it create a linear acceleration? Yes, but an angular acceleration? No, that's not going to generate any torque. Now from B to C, yeah, we've got mg down, we've got normal force up. I'm just looking at horizontal forces here. There aren't any. So there's no linear acceleration, there's no angular acceleration. Now from C to D, when friction comes into play, think about where friction's being applied. It's down here on the very bottom. Now again, all of these have mg down right through the center. None of these are going to create any torque. They all have the normal force going up. None of those are going to create any torque. But this being offset by some distance r, that's going to actually create a linear acceleration. It'll slow this thing down, right? That's why the block in the initial one did slow down, but it's also going to create an angular acceleration. It's going to make this thing start to roll. That angular acceleration means a change in angular speed, which means a change in angular momentum. Now, some people say, well, what about from D to E? It's rolling. So from C to D, it starts rolling. So at part E, the friction goes away. So the torque goes away. So now it stops rolling, right? Well, remember, if it's already rolling, it already has this angular momentum. The only way to get it to stop rolling would be to change its angular momentum again. And that would require an additional torque, a new net torque, which we don't have. So now that it's on a frictionless surface again, it's just going to keep rolling. Right? Think about if you take a bowling ball and you spin it coming out of your hand and it's spinning, spinning, spinning. And that first part of the bowling alley where it's super slick, it just spins, 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 spins. It's not until later in the bowling alley when that the surface isn't slick anymore. So now all of a sudden it starts to change its rotational motion. But you can easily have this thing spinning right along the ice, right along a slick surface, and it'll just keep spinning. So just because the torque goes away doesn't mean that the angular momentum goes away. Okay. So there's an example of how you can kind of navigate your way through one of these problems. All right. I'm going to set you guys up with the first part of Greg's problem for tomorrow. Greg's going to be talking to you about a modified Atwood type scenario. So here's the premise. I'm going to give you 3 slides here. So if you're planning to practice this, take a screenshot of it. Okay. Take a screenshot of the first slide. Both these blocks are starting at rest. The string and the pulley have negligible mass. Friction is negligible between the tabletop and block A, as well as the axle of the pulley. Take a screenshot here. This is the sort of setup. Go ahead and take a screenshot here. This is the first part of the problem. If you're having trouble getting a screenshot of it, you're trying to write it all down, I'm not going to keep it up there long enough for that, but you can certainly go back. Once this recording finalizes, you'll be able to almost immediately go back, and then you can advance through and find this spot, okay? And then here's the next part. Again, yeah, we're drawing and labeling some forces. You may want to actually practice here, draw them, but then also think about how would you describe these? If you didn't have the ability to draw, how could you describe the forces? Right, there's your third screenshot. That's the problem. That's the start of the problem for Greg's lesson tomorrow. So if you want to try and take a crack at that and see how you would approach it from the very beginning, and then you can hear what he has to say about it moving forward. Okay. For those of you that just tuned in for the free response question segment, that's it for me today. I've got a few minutes left. I am going to take just a couple of those and finish explaining. Oh man, sorry, I forgot. I did have one more piece on here, part C. Sorry, 4th screenshot. Sorry, this is how it goes sometimes, right? Take a screenshot here. That's the 4th part for Greg's question for tomorrow. All right, yeah, that's the last one there. All right, just to kind of wrap up, if you were here on Friday and you tried the problem that I left you with, all right, I'm going to keep this fairly straightforward. This scenario, you basically had a student that was swinging or running and grabbing this rope. They're going to swing up and they're going to swing back. And then we're going to change a few things. What if we go faster? What if the student has bigger mass? Or what if they grab from higher above? Well, really, this scenario is actually a pendulum problem. Person grabs a hold of this, they swing up, they swing down, they'll swing over, they'll swing back. That's one full oscillation of this pendulum. Just from here to here, though, that's a fourth of that full oscillation. From there to there, that's a fourth. So going from A to B and then back to A is actually just going to be half of my full period. This equation tells me how I can calculate the period of a pendulum. Well, in this one, how would increasing the speed affect it? Well, this equation doesn't have speed in it, so it's not going to affect it. But how can this be true? I know that the equation says that it's going to be true, but how can it be true? Well, if I run at this thing with a little bit higher speed, this value is going to increase. So I'm going to have more kinetic energy, more total energy, and then I'll have more potential energy when I reach the top. Well, that potential energy, I've got the same mass, same G, so that has to, the only way I'm gonna have a larger potential energy is if I have a larger height. All right, so a larger height, that means the distance traveled, this trip that I take from A to B to A, it's gonna be a larger distance. Well, so shouldn't it take more time? Well, no, remember that you're moving faster. At any equivalent point, you're gonna be moving more quickly. That was the whole thing. This student is running faster. What if I increase the mass? Well, the equation says 2 pi square root L over G, M is not part of it. Okay, so changing the mass won't change the period, so it also won't change T, which is just a portion of that period. But how can this be true? Well, the kinetic energy, now it's the same speed, but I've increased the mass, so I do have more kinetic energy, which means more total energy, which means more potential energy. But remember potential energy. Last time we had more potential energy in the form of a greater height difference. But here, that increase in mass is what gave us more kinetic energies. That same increase in mass gives us the increase in potential energy. This doesn't increase in this case. So this height will actually be the same, which means the distance traveled from there to there, from A to B to A, will also be the same. So you're moving at the same speeds, all at various points, you have the same equivalent speeds, then you're traveling the same distance, so it's the same time, even though the mass is bigger, even though there's more energy involved. Now, finally, if everything else is the same, that means the same horizontal speed and the same mass, but now they just grab higher up. Right, so they run and they jump, and maybe they time it up perfectly so they reach it just at the peak of this little projectile flight, their own little projectile or their little parabolic path, right? So they hit it, and I told you everything else is the same, so it's still the same initial V, but now they're holding on over here. Well, what we've done is we've just changed this variable. We've just changed the length of our pendulum. And if I decrease the length of my pendulum, I'm going to decrease the period. And remember, from there to there, from A to B to A, whoops, went a little far. From A to B to A is half of my total period, right? So if I decrease the length of that pendulum, I'm going to decrease the period. And so then that time, which is half the period, will also be decreased. All right, there's your little analysis of Friday's question. For those of you that were around on Friday, I appreciate you giving it a shot. If you have any questions about that, certainly feel free to grab me on Twitter as well. And then, like I said, Greg's gonna be working on that free response question that I gave you. That was not 3 screenshots, it was actually 4. So make sure you got all 4 of those screenshots, and Greg will pick it up from there. As always, feel free to reach out to me on Twitter. I'll be happy to answer your questions. I'll be keeping an eye on it for the next probably 45 minutes or so. And then throughout the course of the day, I'll certainly reach out to you as well. I know a lot of you have reached out to me at random times, random days, random hours, and I try and get back to them as quickly as I can. So keep them coming. We're here for you guys, and enjoy the rest of your afternoon.